Okay, today we are going to be doing lesson 2.4. Let me share my screen with you. And you can see here we are at lesson 2.4. Yay. So yesterday we talked about what a normal curve was. Today we're going to talk about the empirical rule. I kind of led to that a little bit. So today we're going to talk about using this empirical rule to estimate the proportion of values. Again, this is a whole lot of work smarter, not harder. Okay. So you're going to have to do a little memorization, but it's going to make things a lot smarter. We're going to use that empirical rule to try to estimate a value. Again, these are not life and death situations where we need to be accurate. I just need to know, okay, what percentage of the time is it less than 4 minutes to take the train? And then we're going to use graphical and numerical evidence to determine if a distribution is normal. Now, this might seem a little backwards because the distribution has to be normal to use the empirical rule. But we're going to go through the empirical rule so you can go, oh, that's kind of cool and kind of easy. So, yeah, now how do I determine which distributions are normal so I can apply this process? Okay. So why are normal distributions so important? So we got three main reasons. They're good descriptions for some distributions of our data, and those like examples of normal distributions would be like scores on a test. We have ACT. If you are measuring the same thing over and over again, like here they say a diameter of a tennis ball. Characteristics of biological populations, like we actually do height and weight at ages, male, female, things like that. It could be yields of corn, it could be crickets. And normal distributions, the second reason, they are good approximation to the results of many kinds of chance outcomes. Maybe you're flipping a coin, maybe you're rolling a die. And then when we get to chapters 8 through 11, you're actually going to be able to take data and run tests on it. And those are based on normal distributions. Trust me, you want things to be normally distributed because it makes finding results a lot easier. Okay, so let's go back to our Iowa Basic Skills Test. And we had, the 7th grade student scores. And this is in Gary, Indiana. And you actually did this. We did this in class where it's normally distributed. So it's going to look like a bell. And we were able to come in here and say, okay, directly center is going to be 6.84. And then we add a standard deviation to it and we get 8.39. Then you add another and then you add another. So we would be able to say that 8.39 is 1 standard deviation above the mean. 11.49 is 3 standard deviations above the mean. And to get the 5.29, remember that's where you just turned around and you subtracted. So 2.19 would be 3 standard deviations below the mean. Okay. Now, maybe we have the question of, I'd like to know what percentage of students score a 3.74 or less. So that's this yellow shaded region down here. What's that percentage? Okay. Now, I can look at it and I can tell you that that boundary is 2 standard deviations below the mean. So that boundary line of 3.74, it's 2 standard deviations from the mean, and we want everything to the left of it. Now, what you need to do is you need to calculate the area of that shaded region. And you're probably going, oh, Edwards, I don't know how to do that. No, you don't. That's calculus, okay? That's calculus to do the area under the curve. Now, the rectangle, when we had the density curve, you're probably like, oh, I got that length times width. But this, how am I supposed to do it? This is where we're going to have the empirical rule because it's going to let you estimate really, really well what that area is and not have to learn calculus. Okay. Plus our applet's going to do some of this too. Okay. So calculating the shaded area isn't, like I just said, it's not length times width. Okay. But here's the good part. Does StatMedic do this for you? Yes. Okay. So familiarize yourself. You might need to stop the video. So go to statsmedic.com/applets. But you're going to go down to normal distributions. Okay. You're going to go down to normal distributions. And when you get there in the operation, you're going to put calculate an area under the normal curve. And then you're going to input the mean and the median that's given. You didn't do this. This is given information. And then you're going to click plot the distribution on the graph. Okay. So I want you to play around with that for a little bit. Okay. Now, okay, you should be able to use that. Once you key that in, you should be able to answer these questions right here. Okay, you should be able to look at what it's given you when it plotted those distributions, and you should be able to answer this. Okay, now I'm going to tell you right now, I already know the answers because I have it memorized. And this is what is glorious about the empirical rule. Okay, I can tell you that for this first one, it is 64, 95. And then 99.7. I can't write on this well. Why? Because I have it memorized and it should be right there. 64% of your data will be within one standard deviation. 95% will be within two standard deviations, and 99.7 will be within three standard deviations. That other 0.03 lies outside of three standard deviations. And so that's what's amazing. Okay. Now, this is exactly what I just said. Oops, sorry, 68%, not 64. Excuse me on that. Another book says 64. Maybe I'm wrong. 68%. No, it is 68. Yeah, you just caught your teacher doing something wrong. 68%. So this is the empirical rule, and I actually have this in Google Classroom. I have this graph for you in Google Classroom if you need it, because this you want to memorize. And you can see 68% of all the values are going to fall within one standard deviation of the mean. That's above and below. Okay. 95% is going to fall within two standard deviations. And then 99.7 will fall within three standard deviations. This is the empirical rule. And this is what's great because I don't need to do calculus to find the area under the curve. So basically, if I'm looking for this area right here, this really, really light green, I can tell you that area is 68% or 0.68. Okay. If I want to know this area plus these two medium green, I know that area is 0.95. And then if I want to include these sections right here, that is going to be 0.997. Now these outsides, both of these added together represent 0.03. Okay. That's what's so good about the empirical rule. I don't need to do calculus to find that area. Now it's going to get a little tricky. Okay. So some people will remember this rule as 68, 95, 99.7 rule. You just need to memorize it. Obviously, I need to do a better job of memorizing it because I said 64, not 68. It's 68, okay? So you need to memorize those three numbers. 68% is within one standard deviation, 95 is within two, 99.7 is within three, okay? Now, if you memorize that, we can really quickly estimate the area under the curve, okay? So let's go back to our test scores. A mean of 6.84, standard deviation of 1.55. So we want to answer how many had less than a 3.74 score. We're going to do A first, okay? So let's go back to our normal distribution. We're going to sketch it. We're going to sketch this so we get an idea, okay? We are wanting to know this area right here, okay? This yellow shaded region. Now let's go back to our empirical rule, okay? Our empirical rule says 95% of the data is within two standard deviations. So if we look at the area under the curve, remember all this adds up to 1.0. This section right here, this middle section, is 0.95. So I can do 1 minus 0.95, okay? And that's going to give me, what, 5% left. So 5% represents this area and this area. Now remember, this is symmetrical, so both sides are the exact same. So if I divide that 5% in two, you can see where I get. This upper region is about 2.5%. This lower region is 2.5%. So I can say definitively that the percentage of students that had a 3.74 or below is about 2.5%. Okay. You see how we did that? You got to know that this is 95%. Subtract that from 100%, but then you got to remember it's both of these two tails here, so we got to divide by 2. Okay, and that's not bad. 2.5% of the students falling below, it's a pretty decent number. Okay, now let's look at B. Somebody's coming back and saying, now I want to know how many students were between 5.29 and 9.94. Well, I immediately notice, okay, and I like to draw this in. Here's my mean. My sides aren't symmetrical, okay? The left side is 1 standard deviation away. So here I'm 1 standard deviation away, but this side is how many? It's 2. 1, 2. See, here's 1. So I got 1, 2, and here's just 1. Okay? So how are we going to do this? Remember, the whole thing's 100%. Okay? So if we do this based on 100%, I know this middle section here is 68%. So I can go on ahead on my sheet of paper and go, okay, I got 68% by this middle data right here. This right here, I know for sure is 68%. Now, the big question is, what is this one? Okay. How do I find this one? Okay. So here's what we're going to do. We are going to look at from here to here. I know this is 95%. Okay. I know for a fact this is 95%. But that includes this section right here. I know for a fact this middle is 68%. So if I can do 95 minus 68, all I'm going to be left with is, all I'm going to be left with is this section and this section. So 95 minus all this in the middle is going to leave me with 13.5%, or sorry, 27%. Now, both these green ones that I've circled are equal to 27%. They're equal. They're symmetrical. I only need half of that. I only need half of 27 because I don't need the part on the left side. So I'm going to divide that by 2, and you can see that over here in the math that they've given you. We're going to divide that by 2, and we get this area right here is 13.5%. So now I just need to add 68%, which is that center, plus this one section here, which is 13.5. And I'm going to end up getting what? 81.5%. So this is how you have to look at it. They're like puzzle pieces. If this was an entire puzzle here, okay, if I take this middle section out right here, that's 68%. That's going to leave me with 27% left over. I only want half of 27. That's 13.5. And I got to add those two together. Okay. Now, biggest thing to understand, this 68, 95, 99.7 is only for normal distributions. So when you use this, you're going to see in the instructions, this is normally distributed, or this is a normal curve or normal distribution. And that's kind of a clue. Hey, I can use the empirical rule. Okay. Now, for many of the studies, okay, on automobile safety, this is going to suggest that automobile drivers must make emergency stops and that the stopping distances are modeled by a normal distribution. Okay, so we are going to talk about a car traveling at 60 miles per hour under typical conditions on drive pavement. Okay, now here's the key. It says the distribution of stopping distances is approximately normal. Bells should be going off. I can use the empirical rule. Here's my mean, and here is my standard deviation. Those are important. So what is going to be the stopping distance at the 84th percentile? Justify your answer. Guess what? Okay, we can draw this out. And so if we look here, Mean is 169 feet. My standard deviation is 4, so I'm adding 4 each time, and then I'm going to subtract 4, okay? They want to know what stopping distance is at the 84th percentile, okay? So it can get kind of tricky here, okay? Because there's going to be a way we can do this in the calculator, but what I'm basically going to do is I know that there's 68% in this middle section, okay? 100 minus 68 leaves me with 32. And this is kind of like a trial and error. So that means that this blue shaded will be 16% and the non-shaded is 16%. Okay, because 34 or 32 divided by 2 is 16. Well, what is 16 plus 68? Well, it kind of falls perfectly at 84%. Okay, and so that's going to tell me if all of this is 84% of the data, then 169 is the 84th percentile. Okay. So we would say 84% of cars would stop in less than 169 feet. That's how we would interpret this. We could also go here if you wanted to sit here and do this one. Remember, this would be at 95% if we did the whole thing. So 100 minus 95 would tell me that this is 5%. So we would be able to say that, no, this is 99.7, 95. Yeah, this would be at 95%, but then I need to add in this 0.25. You can then turn around and say, what is it? 97.5% would stop at 173. And then you would be able to say that 9.7, it's a 0.015. 99.85% stop at 177. Okay, now, again, how do we know normal distributions? ACT and IQ scores, gas mileage, weight of the same thing that we're measuring, heights of 3-year-old girls. Here's an example for the normal distribution of the height of the 3-year-old girl, okay? You're going to make it, again, you go back here, you're going to make it look like a bell. You got the mean in the middle, and then you've got your standard deviations as they go out. Now, distributions of other quantitative variables can be skewed. We would say they are not normally distributed. We could talk about single home prices in a certain city because, again, like, you got starter homes or you got these mansions over here. Okay, survival times of cancer patients after treatment. Those could be skewed, not normal. Number of siblings for students in the class. Again, those could be not normal. You could have an outlier. Somebody could be 19 kids and counting. So the ones we talked here, these distributions would be right skewed. Okay, now, why would these be right skewed? Think about it. If you start asking about how many siblings, you're not going to have somebody that comes back and go, oh, I got -2. Yeah. They're going to be like 1 or 2. And then again, it's going to be right-tailed because, yeah, you might have somebody that has 8 or 9 siblings. But those would be outliers. Most people have, the average is 2.5 kids per household. Now, it is very, very risky to assume that our distribution is normal unless we analyze the data first, okay? So, first, we started this in chapter 1. We're going to graph it first, and then we're going to add the numerical summaries to assess it. And again, we didn't do this by hand. We did this in Statsmetric, okay? If the graph is clearly skewed, has multiple peaks, or does not look like a bell, we would say it's not normal. And again, you're going to go back and do that dot plot or the histogram to do this, okay? You're not going to use a box plot. However, if the graph looks roughly symmetrical and bell-shaped, okay? Even if it looks roughly, we still can't assume that it is approximately normal, okay? But the empirical rule can give additional evidence in favor of or against whether it's normal, okay? So let's That's probably all Swahili. Let's look at this and actually do an example on it. Here we got a dot plot. We got 77 brands of breakfast cereal, and we are talking about the caloric intake on the cereal, okay? So we can look at this. It looks roughly symmetric. It does have a single peak. It's somewhat bell-shaped. But the one thing I'm noticing right here, ooh, I got a gap, okay? So we are going to check to see if this falls within the empirical rule. If it falls within the empirical rule, then we can say it's normally distributed, okay? So we're going to calculate the percent of data values within 1, 2, and 3 standard deviations of the mean. Again, here we have the mean and the standard deviation through our applet, okay? So mean plus and minus 1 standard deviation, that's going to give us that first numbers. Okay. Now we're going to do 81%. Okay. We went in here. How are they getting 81%? They calculated. They went 1, 2, 3, 4, 5, 6, 7. They counted all the dots. There's 63 out of 77. So that percentage is 81.68. What's it supposed to be if it's the empirical rule? 68%. Let's test it with 2. Okay. 2 standard deviations is going to be 67 to 145. That's giving us 92.2. And remember, within 2 standard deviations, it should be what? 95. Okay. So the first one was high. This one's a little low. 3 standard deviations, they're going to count the dots. Okay. And we get 100% of the data. What should it be? 99.7. Okay. So would you think this would make it approximately normal? What do you think? Again, look at the first one's high, second one's a little low. Within 3 standard deviations, it includes everything. Okay. It's going to include everything. I'm going to say no, it's not. Yeah. Okay. No, because that 100%. Okay, now let's look at our example here. Now here we've got Oreo cookies, and is this normally distributed? So what I'm going to do, here's the data. I'm going to put all of this in StatMedic, and I'm going to get that number summary. 1 quantitative variable, single group. Okay, and you can see down here at the bottom, here is my 5 number summary. These are my summary statistics. I also in StatMedic made it do a histogram. So if I'm looking at this histogram, does this look bell-shaped? Roughly symmetrical, sort of. I got 1 peak, okay? But does that necessarily mean it's normally distributed? Not necessarily. So let's use the graph and the empirical rule, okay? So if we look here, okay, and we do 1 standard deviation of the mean, we get about 71.1%. Within 2, I get 95.6. That's really close, okay? And then 3, I get 100% again. Would we say this is normally distributed? Okay. Those close are very, very, very close to 68, 95, and 99.7. So even though it has the 100%, we would say that this is numerical evidence that it's approximately normal. Now, the last one I said, oh, it's at 100%, probably wouldn't count it, but it was also because that first standard deviation was really, really high. These are really close. So yes, I could say this one's approximately normal. Again, all 3. This is really close to 68. This is really close to 95. This is close to 99.7. But when I had 100% and this one was really high up at 83, I would say it's not normal. Okay. Okay. Now, again, we're never going to say that it is normal. We're going to say it's approximately normal because for it to be normal, it's got to be perfectly symmetrical. Okay. And just get it in a rule of thumb. When it comes to statistics, we hardly ever say anything is for sure definitively. We usually do approximately estimated. Okay. Now, here we go. Here's our random sample of 45 double stuffed Oreo cookies. We determined that it's approximately normal. Okay. So when we do these random samples like this can allow us to generalize it to the entire population of Oreo cookies, not just the 45 that we looked at. Okay. So it is reasonable to believe that the distribution of the amount of stuff in the Oreo cookie is approximately normal. Okay. We could turn around and take the data that's right here and apply it to every packet of Oreo cookies. Okay. And so, did we use the empirical rule to estimate the proportion? Yes. Did we use the empirical rule to estimate the value? So, like, that was that drive time one at, what's the speed? Or no, it was how many feet will it be if I stop given that percentile? And then can you take data and determine if it's approximately normal? And again, you're following that empirical rule of the 68, 95, 99.7. All right. Go ahead and you can stop the video and get started on 2.4. And hopefully you are enjoying it. And I'll see you when I get back.